Okay, so we're going to talk about the root test in this video. We're still working through section 11.6. The idea here is fundamentally not that different from the ratio test. So we're going to take another limit of some other function relating the terms of a series. We're testing a series for convergence or divergence, and we get something better again. We get either a test is convergent, absolutely convergent, I should say, or divergent, or the test is inconclusive, just like with the ratio test. So here's the idea. I'm going to find for a series a sub n, we evaluate the limit, capital L being the limit as n goes to infinity of the nth root of the absolute value of the nth term. So in other words, to think about what we're doing here, we're looking at absolute value of a sub 1, square root of the absolute value of a sub 2, the cube root of the absolute value of a sub 3, and so on. And supposedly, not supposedly, I mean, we know that it works. It's pretty well known to be true, and we can apply it and we'll use it. This gives us the same sorts of cases that we have for the ratio test, which is if L is less than 1, the series converges absolutely. So as long as this limit exists and is less than 1, this converges absolutely. If the limit is greater than 1 or is infinite, then the series diverges. Not even converges conditionally, just diverges. Case 3, if the limit is equal to 1, so this L is equal to 1, the test is inconclusive. It is inconclusive in the same cases as with the ratio test. So if the ratio test gives you L equals 1, don't try the root test. Vice versa. If the root test gives you L equals 1, don't try the ratio test. Use a different test. And we can use the same examples as we did in the previous video to see that why this must be true, right? So the harmonic series, for instance, you'll notice that the L will equal 1 because you'll get 1 over the nth root of n. And L will equal 1 also for the series with the terms 1 over n squared, the inverse of reciprocals of the squares. So we get the same kinds of cases, and just like with the ratio test, when we find this limit, we'll just sort with between which case it is, and then that'll tell us whether the test converges or doesn't converge. Why would we use the root test over the ratio test? Usually if we involve some series that has some nth power of something, right, then this will be helpful. And so I think it's best to just think about a few examples. So let's just see some examples. So I'm not going to justify this root test. The proof and the proof sketch roughly run just like with the ratio test. Because the limit is greater than 1 or less than 1, there must be something true about this expression here. So this expression here, something beautiful happens to that. And okay, I'll just briefly justify it, right? So in case 1, right, it'll look like the nth root of a sub n is less than 1. Or actually, we'll call it less than r. And so a sub n, if you rearrange this inequality, the absolute value of that is going to be less than some r sub n. Compare it to a nice convergence geometric series, and so on. Similarly, in the divergent case, right, because this limit is going to be greater than 1. Then at some point in the tail, the terms look like this, and so you end up with something like this, but 1 raised to the n power is greater than 1. So in the divergent case, you eventually get your tail, the terms are going to be greater than 1, which means, of course, it can't converge to 0. So by the divergence test, the series would diverge. If you want me to talk about that in any detail, feel free to ask me. But it runs roughly the same. Let's see an example. Does the series starting at n equals 2 of -1 raised to the n minus 1 over ln of n to the n converge or diverge? So this is where it's helpful because, one, it helps us deal with things in terms of the absolute value version of the series, so we don't have to worry about any pesky alternating parts of the series, or we can just focus on the nth root of 1 over ln of n to the n power. And because of the n power here, that's going to cancel with the nth root, and we just end up with something like limit as n goes to infinity of 1 over ln of n. Now, ln of n as a sequence diverges to infinity, which means the sequence 1 over ln of n will converge to 0, which is less than 1. Since L is less than 1, it's equal to 0, the series converges by the root test, right? Okay, let's see another example. Use the root test. Sometimes you'll be asked to explicitly use the root test, sometimes you won't. But in this video, it's my objective to show you how the root test works. So of course we're using the root test, but sometimes you may be actually directly asked to use the root test. We're going to determine the convergence or divergence of the series from n equals 1 to infinity of 1 plus 1 over n raised to the n squared. Okay, so you may notice some familiarities here. Don't get too carried away yet, because some interesting stuff is going to happen here. So we have the limit as n goes to infinity of the nth root of 1 plus 1 over n raised to the n squared. Okay, so something fun happens here. You'll see it in a second. So the limit as n goes to infinity of 1 plus 1 over n raised to the n squared divided by n, because we're converting to rational exponents here. Now n squared divided by n is n. 1 plus 1 over n raised to the n. Oh, look at that. Well, we know what this sequence converges to. And this is e. E, the real number, Euler's number, is greater than 1. By the root test, this series diverges. Okay, I'm calling it a sub n just because I didn't want to write out the whole series, but there it is. Because that limit is greater than 1, the series must diverge by the root test. So again, pretty easy to work with. Your utility is going to happen when you have terms that have powers raised to the n power. So if something's raised to the n power, use the root test. If you have ratios that look nice, right? So repeated products, you have factorials, then you would want to use the ratio test. And we're getting into the next video, which is, can we develop a general strategy for testing series? And the answer is yes, we're actually going to have talk about that. So, but that's the next video and the next section. So we'll stop here.